Alright, so this is the first video of a three-part series on how to do basic vector addition and subtraction. This video is going to be it's going to be just about the triangular method. And to start out with, I'm going to give us two vectors. So our first vector is going to go, let's put it here, I guess, and we'll make it go down. And let's say this is just 100 miles per hour, we'll say. Why not? Okay. And then we're going to have a second vector, and I'm going to make this one a different color just so we don't lose track of them in our math. And we're going to have this guy go, let's say he's going to go straight up, like this, do this, and so that's 5, this is 5, that's why I, okay, so we're going to do this, and then let's make them proportional. So that if this is 4, that is 400 divided by 5, so 80. So this is 80 miles per hour. Okay, so we have two vectors. And the reason why I wanted to make sure they were to scale is because this method is contingent on trig. And in order for us to do trig properly, we need everything to be to scale. So this method is also called the tip to tail method. And it is where we take our first vector, so that 100 miles an hour, and we tack it on, or we start the next vector from the tip of the first one. So we take that 100, that vector, so 3 over 4 down, this, and then we take the second vector, and the tail of the second vector goes onto the tip of the first vector. So it's going to go here. Okay? Does that kind of make sense so far? I'm actually going to do some slight alterations here. We're going to make this, let's make this 120. So if this is 1, 2, 3, 4, let's do this. So this is 120, which means this guy is going to go up to 6 here. 1, 2, 3, 4, right there. Perfect, because I wanted to avoid you making that right triangle. So this is 100 and this is 120. So the resultant vector in this method, because we are essentially adding these two vectors together, the resultant vector is the vector that goes from the tail of the first vector to the tip of the second vector. So this is r. Okay? And in this method, we want to find the magnitude of the resultant vector, and we want to find this angle. Luckily, we can do that with a bunch of trig. So this is a triangle, which means we can use law of sines and law of cosines and all of that fun stuff to get everything we need to know. And we can use the fact that all of the interior angles sum up to be 180 degrees and all of that. Now we cannot use Pythagorean theorem because our angle is not a right angle, or our triangle is not a right triangle. And for the sake of going quick, I didn't include the units here, but in practice, be sure to include them. You don't have to include them like when you're doing this to help you kind of visualize and work through the problems, but if you're doing it for an assignment or something, be sure to include units. Just put that out there. I know a lot of physics professors, and especially, and like if you go on to STEM heavy courses that require this kind of knowledge, units will save your life. Like you'll get into such like intricate and complex math that if you lose units, you are likely to start getting things wrong because your unit should cancel and all of that fun stuff. But that's way in the future. But just be aware that units are your friend and include them wherever you can. Okay, now, because this is trig, because we're about to do trig to find that theta and that r, and we can't use Pythagorean theorem to find r. We can't do r equals the square root of 100 squared plus 200 plus 120 squared. We can't do that because it's not a right triangle. But we can find this guy. I'll use a different, we'll label this one like that. Okay, so if we know that if we go back to look at our vector over here by itself, I'll zoom him in quite a bit. I don't want to get too busy on top of that. We know that this guy goes over 3 and then down 4. So this angle right here is the tan inverse of opposite, so 4, over adjacent, or 3. And that equals 53.13 degrees. And then some more numbers, but we'll just round it to 53.13 for now. So if we go over here, this angle is 53.13 degrees. Now, this whole angle is 53.13 plus theta. Okay? But we are on the right track. So if we cut this right here and make this a right triangle, we can find what this angle is. Okay? Make sense so far? So if we start there, we can find what that green theta is. So, and since this is a right triangle, we can use Pythagorean theorem if we were so inclined, although I don't think you can use it for angles. I misspoke there. We're going to do the, all of our angles summed up equal 180. So 180 degrees equals 53.13 plus 90 degrees plus green theta. So then theta becomes 36 point something. 180 minus 90 minus 53.13 is 36.87. Okay, so 36.87 degrees. So we're getting somewhere now. This is where Pythagorean theorem is going to come into play. Or before we do Pythagorean theorem, we'll do law of sines actually. So we know the magnitude of the hypotenuse. It is 100 miles per hour. And we know all of the angles. But we still have that other right triangle. So this right triangle up here, we still have that other right triangle we need to solve for. Because the resultant vector that we're looking for is the hypotenuse of that right triangle. And in order to do that, we need to, at the end of everything, we want to find what the magnitude of this horizontal line is. And that is considered the x component of the blue vector. Later on, these things will just start being called x and y components, okay? So we need to find the x component of the blue vector, so the 100 miles per hour. We can do this a number of ways. So there's one way, which is SOHCAHTOA. So if we do SOHCAHTOA, we can find what that green x component is using SOHCAHTOA, or we can use law of sines. Either one. We will use, I guess we'll do both methods actually. So because we know the hypotenuse, we have to use one of these that includes the hypotenuse. And I'm going to use that 53.13 as my angle. So if we want to know the green line, the x component, it is adjacent to our blue angle, to our light blue 53.13. So since it's adjacent, let me use a different color. Since it's adjacent, we should use cosine of theta equals the adjacent over hypotenuse. So cosine of 53.13 equals the adjacent divided by 100. And now we solve for the adjacent. And that should be, let's see here. So we do cosine of times 100, we get 60 miles per hour. Okay, and it is the same unit as our hypotenuse. So this thing right here is 60 miles an hour. Okay, now we know the x component of our blue triangle. We also want to know our y component. And I guess I will use this color. So we want to know this guy. I wonder if let me think. All of these colors are really similar. What if I pull out a nice yellow? So we want to know this guy. And we could find it using the SO part of SOHCAHTOA, but I'm going to use law of sines for this, okay? Just to show you a different method. And this becomes the sine of an angle divided by the opposite side equals the sine of another angle. Oh, no, this should be lowercase, divided by b, and then over big C. Okay, and where this is A, and this is A, and this is B, and this is B, and this is C, and this is C. That's the law of sines. So we are looking for B. So we're going to use this thing. We're looking for uppercase B. And whenever possible, use all of the given values. Okay, so we found this number and we found this number. So there could be rounding error in that. And to avoid too much rounding error, wherever you can, don't use the numbers that you found, use the numbers that were provided in the question. So we're going to use the sine of 90. Okay, no, first we're going to go on a little joyride. So the sine of A, which is 90 degrees, divided by 100 miles an hour equals the sine of 53.13, and we have to use that because that is opposite of the side that we want to know. Does that make sense? So we could have also done the sine of 36.87 divided by 60 because those are two angles. So that 36.87, we found it. We also found that 60 degrees, or that 60 miles an hour. Because we found both of those, we're not going to use that because that degree right there, I know I rounded. Okay, so now we're going to do B sine of 90 equals 100 sine of 53.13. And then divide all of this by sine of 90, and we get B equals 80 miles per hour. So this is 80 miles an hour. Okay? Now, we've solved half of it. And the next half is a little easier. So if this whole line right here is 120 miles an hour, and the segment from here to here is 80 miles an hour, that means I guess, okay, we'll use this color. That means this right here is 120 minus 80, which is 40. So that is 40 miles an hour. Okay, are you starting to see what we're gonna finish out here? This is a right triangle. So this, all that is a right triangle right there. And ooh, okay, let's not do that. That is a right triangle. And we know that this side is 60 degrees, and we know that this side is 40 degrees. And since it's a right triangle, we can, not degrees, sorry, miles an hour. Since it's a right triangle, we can use the Pythagorean theorem. So we get r equals the square root of 40 squared plus 60 squared, and that equals the square root of 40 squared plus 60 squared, and it is 72.11. Okay, that's not an 11, that's a 16. So 11 miles per hour. That is the magnitude for, where's my mouse? Hello, okay, whatever. That is the magnitude for the resultant vector. Now, we have found one of our things that we're looking for. We still have to find theta. And we can do that by using SOHCAHTOA, law of sines, law of cosines, any of that. I'm going to use SOHCAHTOA, okay? Because that r that we found, so 72.11, that r that we found, I rounded. It's a never-ending decimal. And because I rounded, I want to avoid using it just in case it skews our theta. It skews our degree. And if I use SOHCAHTOA and I use the TOA version, or the TOA part of SOHCAHTOA, I completely avoid using a rounded number because we get the tan of theta equals opposite, so 40, over adjacent, which is 60. So then theta equals the tan inverse of 4 over 6. Okay? We can plug that in to our calculator and get theta equals 33.69 degrees. And the magnitude is 72.11 miles per hour. Okay. And that is the triangular method. So we started out with our two vectors. We put the tail of the second vector onto the tip of the first vector, and we drew the resultant vector going from the tail of the first vector to the tip of the second vector. And the vector, the resultant vector, will always, as long as you're adding, the vector will always go towards wherever you ended up. So it will start at the beginning. So the tip of the resultant vector, or the tail of the resultant vector, will be at the tail of the first vector. Okay? And then you just figure out, all of that fun stuff. Now, this method is possible if you are adding, more than two vectors together. You just keep adding them on. But when that happens, I would recommend using the method that is covered in part 3 of this series. I've found that one is probably the easiest and the most applicable to, everything. Both parts 1 and 2 of the series, the methods covered there are very, very specific and not very applicable. But they are geometry based as opposed to algebraically based, which is give or take whichever ones you're more comfortable with. But I hope that kind of explained the tip-to-tail or triangular method a little better, and I hope to see you in part 2. If you have any topics you want me to cover, feel free to leave a comment. I'll get to them eventually, probably. And see you in part 2.